Pass at unsupervised learning was to understand how we can dissect the data, right? Basically, how we can form clusters, model it using Gaussian mixtures, etc. Our second pass that I'm going to talk about now is, can we now phrase unsupervised learning in a way that we can not only try to potentially summarize the data, but also perhaps to generate artificial data that looks like the real data. For example, artificial images that look like real images but are purely generated sort of randomly. In addition, we would like to implement these techniques using deep neural networks and leverage the software infrastructure that we already have for training such networks in the context of supervised learning. So basically, if we can define the right cost functions that we can train using backprop for unsupervised learning, then we can leverage this entire infrastructure. So let's discuss two approaches that are quite different in philosophy that actually work quite well for these purposes. The first one is the variational autoencoder. Variational autoencoder, or VAE. The second one is generative adversarial networks. That's GAN. So the variational autoencoder, well, sort of autoencoders more generally are the following setting. Basically, you have an encoder that takes the data and maps it, embedding the basic assumption underlying this is that there is even though the data can be in a very high dimensional space, there is a latent vector. So this is often also called a latent vector of lower dimension that captures the essential features of the data. So there's an encoder like that, and if the latent data actually captures essential features, then I should be able to generate some version of the data from it. So I also need to devise a decoder that takes the latent vector and outputs something that is in the data space. So I'm going to call this X hat, because you can put X through the encoder and get a latent vector, and then you put that same latent vector through the decoder and you won't get exactly X back, right? So obviously I've lost some information in going that way. So this is sort of X hat, right? So that's a generic autoencoder, right? And there are many different approaches for constructing autoencoders. The VAE has a particular approach that I'm going to discuss in more detail in a bit, but basically I'll just say that the encoder is assumed to produce essentially a probabilistic map from the data space to the latent space, and the decoder also is a probabilistic map from the latent space to the data space. And we choose these maps so as to maximize the likelihood of the data we are seeing. So that's the big picture approach of the VA. And while we are talking about encoders and decoders, how would we use these? Well, I mean, of course, the encoder, you can think of it as sort of a dimensionality reduction or summarization. That you can think of very directly from the encoder, right? The more interesting and new part that have happened both in the context of VAEs and GANs is that if I can ensure that embeddings come from from a simple distribution. So, for example, I can, for example, say that let me try to make sure I design my encoder so that the embeddings come from a simple distribution like a zero mean white Gaussian thing. Then I can feed this randomly generated vectors to the decoder to get artificial data, right? And how well I design the encoder and decoder will determine how realistic this artificial data looks, right? And how good my dimensionality reduction or summarization is would be again determined by how well these things are designed, but also what my downstream tasks are. For example, I might have semi-supervised learning where the number of labels available is not that many, so you have a lot of unlabeled samples and a few labeled samples. If I'm working in lower dimensions, I might be able to do better. Or I could do clustering afterwards in a lower dimensional space. Clustering and mixture modeling becomes more feasible. So there's a bunch of this part, the dimensionality reduction part, is something that people have thought about for forever and come up with lots of designs for. This generative part, where I generate fake data, this part is new, and this is the aspect of it that has actually intrigued a lot of people, because taking random numbers and coming up with images at the output is a pretty interesting concept. So it's fair to say that sort of the VAE framework, which is what we are talking about here, is a new twist on a fairly well-established autoencoder concept. Now, GANs, on the other hand, are a completely new concept introduced a few years back, in 2014 by Goodfellow et al. And that basically says, I won't worry about the embedding at all. I'm going to try to generate fake data directly. So the concept of GAN is, I'm going to come up with a generator, G, which takes latent vectors from some nice distribution. Suppose I say Gaussian with zero mean and white covariance, right? That's basically equivalent of a decoder, and that generates artificial data, G of C. And I don't worry about the inverse mapping, but I say, look, I'm going to train something that tries its best to distinguish between this artificial data and real data, right? So this is what they call discriminator, D, right? And that'll output some estimate y hat, as usual, of whether it is real or fake. So this is the fake data, this is the real data that I'm feeding in. This is, say, I put a label to it, y equals 1. I put a label to the fake data, y equals 0. And I want to, and training the discriminator is a standard sort of supervised learning problem. I train it to, say, minimize the cross entropy, right? So that's all well and good, but then the generator is trying to fool the discriminator. So the discriminator and generator are playing a game against each other, and the discriminator is trying its best to distinguish between real and artificial data, and the generator is trying its best to generate artificial data that can fool the discriminator. So there is no attempt to summarize the real data into an embedding or anything like that. I directly try to generate artificial data that will fool a discriminator. Now, there are modifications to GANs that will also be able to generate embeddings, but we'll mention that briefly at the end. So that's the idea behind GANs. And now we'll get into more details for each of these concepts. Remember that our goal here is just to provide sort of the roadmap to the basic concepts. There's no substitute for going and reading the original papers. That you should do anyway. But hopefully these discussions will provide a background useful for parsing through those papers.